voltage is a difference of potential. It means on the input side, things are backed up, and on the output side, things are a little bit lower in some fashion. In this case, it's potential. And this open arrow is how we symbolize voltage. Now, Greg talked about something last week without explaining something that I would have explained about it, and that is which direction current flows. The electrons that are in every molecule, these little things with a negative charge that surround the positively charged nucleus of an atom, are in every molecule, and they get stolen by some electromotive source with a positive charge. The negative electron gets attracted to the positively charged place, and then it gets replaced with another electron from another atom further down the chain. And it keeps going all the way down the chain until you get back to the origin of the source, the battery, which provides a flow of electrons. So you get electrons flowing out here through the conductor and back to the other terminal. The electrons, which are normally thought of as the current in the wire, are flowing one direction. But the current, as Greg pointed out, is flowing the other direction. It's going from plus to minus. Why is that? What he didn't mention last week, and I'm mentioning now, this is a simple answer: convention. We arbitrarily, I really mean arbitrarily, could have gone either way. The mathematicians say if you go negative with everything, we're going to have a negative sign in all of our mathematical terms, and it's just cumbersome. So to make life simple, we're going to snap our fingers and say, by convention, current flows from plus to minus. Don't argue with us. That's just the rule. Everybody said, okay, we have it that way. There's a vacuum too. This thing called a cathode emits electrons. They're attracted to this very high voltage plate. They're regulated by the screen in the middle called a grid, which controls the space charge in the tube and allows a tiny current here, alternating, to become a larger one here. The little voltage swing here produces a large voltage swing there. But guess what? The current is flowing that way, even though the electrons are flowing the other direction. Strange, but that's just something you have to get used to because them's the rules. There's no other way to explain it. Okay, so you had a difference in pressure here.
Rich,
Yes.
sounds like a good time to interrupt you.
Go, please. Well, as often as you can, interrupt me, because if I lose you, I'm
You
going
were
to
on a
go.
nice roll.
And questions that keep me going. They help me.
I don't know how much this takes, but I thought resistance was rho L over L. So how does that turn into over A squared?
This is just a way of describing a conductor, wherever I put it.
That's your rho, right? Your resistivity?
Rho is just, it's a character in the Greek alphabet that was chosen to symbolize the coefficient in the material that defines how much it takes to get current to flow
I
through
know what
it.
resistivity is.
Yeah, okay, so I mean, let's just leave it at that. And then the cross-sectional area says the more material you got, the more, which are really more parallel paths. And you learned last week that parallel paths reduce resistance. The less ohms you're going to get in the path that you're going to take with the current flow. Anything about that that doesn't fit?
Yeah, it didn't answer my question, but...
Try it again.
Because the formula is resistance equals rho times length of the wire over the cross-sectional area.
Oh, yeah, you know what you were talking about? If you want to say, okay, where do we get R in ohms? This is the resistance per unit of measure.
Oh, I
per
see.
foot. I didn't say that, yeah, times the length. You are absolutely correct. Because obviously the more wire you have, the more resistance you're going to have. This is just per equal segment of resistor. If you happen to have a piece of wire and it's 10 feet long and it's 10, and then you make it 10 times that, you're going to have 10 times the resistance.
Okay.
So yeah, you're right. Well, length is part of that. I was just talking about part of where it comes from. I left that out. You're right, very good. Good catch. So here's what I want you to think. Whenever you see voltage, add a word to it. Voltage drop. Because really what it is the potential difference, voltage and potential difference, between the high and the low side. So you don't really think of, even though they use volts to measure this voltage source, it's really an electromotive force that starts the process going. The result is a voltage drop when you push that current through something that impedes the flow of that current. And what you're going to get is a drop in the potential from the input to the output side of that thing that you're pushing the current through. Just like you're going to see a drop in pressure from the input to the output side of this guy. Just a conceptualization. Okay. Okay, let me try to think of what else you talked about that I wanted to kind of patch up on. Oh, I know what it was. We're talking about impedances in general. And Greg got into the fact that they come in different styles. One kind of impedance is called resistance, and one kind is called reactance. I just want to build on that a little bit. And we're going to do that by drawing a little tree. Because these things come in subparts and subparts and subparts. At the top of the tree, I'm going to put the letter Z, as in Zed, Zulu. And that letter is going to stand for impedance. It is not going to stand specifically for resistance, inductance, or inductive reactance, or capacitive reactance, but those are going to be components of it. The impedance that you see here, here's your electromotive source, and here is your voltage drop, and here's the current that flows through, completing the equation that you saw last week called Ohm's law. This voltage drop is equal to that current flow times whatever value that resistor happens to have. So over on this side of the tree, we have this thing called R. And it is called resistance. And it's measured in ohms. And it's got some symbology, the letter omega, last letter of the Greek alphabet. Learned that from being in a fraternity house. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta. You know that. Phi, chi, psi, omega. Anyway. R has time invariance. You're going to say, what in the world is that? Well, the key is the word invariance, meaning it doesn't vary. That resistance will be the same whether it's an AC or a DC circuit. And it doesn't matter if it's a low frequency AC or a high frequency AC circuit. If that resistor is 1,000 ohms, it's 1,000 ohms no matter what. And it's symbolic. Schematic symbol looks like that, a zigzag line, indicating you're going to go through something that's going to make life difficult to get from this point to this point. That's resistance. On the other side is the letter X. Where'd that come from? That is reactance. It's another kind of impedance. Resistance is a form of impedance, reactance is a form of impedance. And it, by the way, has two flavors. One of them, X sub L, the other, X sub C. The C is for the capacitor, symbolized with these two parallel lines, which really is a good graphic because it shows you pretty much what a capacitor looks like functionally. It'll accumulate charges on one plate that are opposite the charges of the other plate, and it will store energy doing that. And this is X sub L. Greg used the word coil. Well, I use the more broad term, inductor, or inductance, just like the word over here is capacitance. This stuff is time variant. It does matter if it's AC or DC. In fact, if you put DC on a capacitor, it'll charge up and current will not flow through it anymore. It just charges up and blocks current flow from that point on. With an inductor, if you put direct current through it, it really doesn't matter that much. For a brief moment when you turn it on, it will do something interesting, which we'll get into a little bit later tonight. But after that, the current will just flow on and on like the Energizer bunny forever and never change. So these guys, as it turned out, have absolutely perfectly opposite characteristics. Capacitor does one thing, it stores energy in an electric field. An electric field is wherever you have opposite charges facing off against each other. Between that electric field, I'm going to draw a little arrow here, to say that's an electric field. You got a plus charge on one set of plates and a minus charge on the other set of plates, meaning one's got electrons in surplus and one has electrons in deficit, having a net positive charge because you removed electrons from atoms. You have the essence of an electric field. An electric field is a nice place to store energy. In an inductance, you have energy stored in a magnetic field. Because, as we'll also talk about a little bit more tonight, whenever you have a current flowing through a wire, you will have surrounding it, this is the current flow. This is something, I use the letter H, and it does not stand for Henry's. It's a general term used for magnetic flux, the flow of magnetic field. Whenever you have current flowing through a wire, you will get a magnetic field around it. So what you have in this inductor is this magnetic field, just like a bar magnet. When you turn off the current, the magnetic field goes away. But when it goes away, it does something very interesting. The transition points, meaning when the current flow turns on and then the current flow turns off, does very interesting things in an inductor. And if it never turns on and never turns off, it does what alternating current does, where it starts out, here's the plus and here's the minus part. It goes like this. It goes to some peak positive value and some peak negative value, crossing zero twice. In that alternating current scenario, this thing is constantly changing, and then all of a sudden the inductor does some magical things. It starts impeding. The faster that alternation or oscillation takes place, the more it impedes. Ironically, the more the alternation of charging this capacitor happens, the more it conducts. It impedes less. Perfectly opposite characteristics, and I'm going to explain why that is, because we're going to get into each of those two devices in some detail. But here's the big picture. Z is impedance, R is resistance, X is reactance. X has two flavors, inductive, X sub L, capacitive, X sub C. They not only have this difference being time invariant here, it doesn't matter if it's AC or DC, it does the same thing. Time variant here, yes it matters if it's AC or DC, and how much AC, meaning how fast it oscillates, whether it does it at a slow rate or at a very rapid rate, changes how much impedance it creates. And I think what there was about that I wanted to point out. Oh yeah. Another characteristic that's important here is this thing will dissipate power. Meaning whatever current flows through it, and Greg last week told you that power is equal to whatever voltage is across it times whatever current is across it. So you got this voltage here and this current here. If you multiply the two together, that's how many watts power you're going to get. What happens to that power? It warms up the resistance. So what does the power do? It converts energy that's electrical into energy that's thermal, and down the tubes it goes, meaning you waste it. If you had an incandescent light bulb here, you know things get awfully hot. You wouldn't want to touch one that's been on for a while, especially a large one. So this thing's not just generating light, it's generating heat. Resistors do that. That's supposed to be there. This guy does not dissipate power. He stores it. Or actually, to be more correct, he stores energy. What's the difference between energy and power? Anybody know?
Time.
Time, exactly. Power is energy per unit of time. It's the rate at which energy is either created or consumed. So when you get an electric bill and you're charging kilowatt hours, you are paying for energy. A watt is a unit of power. It's the rate at which, it's a joule per second to be exact about it. It's how fast this energy is either created or consumed. And if you take energy per unit of time and multiply it by time, that's what kilowatt, thousands of watts, which are joules per second, and multiply it by time. You're canceling out the time, you're only leaving the energy part. A watt hour. Is energy per unit of time. That's this thing multiplied by time. And we know from high school algebra that those things cancel out. Something in the numerator, you can divide the numerator and denominator by the same values and sort of take them out of the equation. In doing so, you're paying for energy. You're paying for the energy part when you have kilowatt hours on your bill. All right, so this guy